Hi, this is Qiao at Lehigh University. Today we are going to talk about the homework 6. Let's take a look at the first problem. A pump delivers water from reservoir A to reservoir B. We know the water surface elevation in reservoir A is equals to 47.5 meter, and the water surface elevation in reservoir B is equals to 55.9 meter. We know the friction factor, length, and the diameter of the pipe. And in this problem, the minor losses can be negligible, which means that the head loss is equals to the friction loss. The problem also provided us the pump characteristics. It asks us to calculate the flow rate and the velocity. To solve this problem, we need to use the system curve equation. The system head is equals to the water rise plus the head loss between the two reservoirs. Let's calculate the water rise first. Because we already know the water surface elevation in the two reservoirs, so the water rise should equals to the h sub b minus h sub a, it equals to 8.4 meter. Then the next step is to calculate the head loss. Because the minor losses can be negligible, then therefore the head loss equals to the friction loss. It equals to K times Q to the power of M. Because based on the information given in table 3.4 for Darcy-Weisbach equation, we can know that the M equals to 2, and based on the given information, the value of the friction factor, the length, and the diameter, we can calculate the value of K. It equals to 78.5. We already know the value of M and K. Then we can use these two parameters to represent the head loss. It equals to 78.5 times Q to the power of 2. So currently we have the water rise and the friction loss. Therefore, we can represent the system head. It equals to the 8.4 plus the 78.5 times Q to the power of 2. Because in the head loss, the equation to represent the head loss and the equation to represent the system head are all includes the flow rate Q. Then we can bring the flow rate in the pump characteristics table into these two equations to get the value of the friction factor and the system head. So the next step is to summarizing the information into a table and to determine the flow rate, and then to calculate the velocity. So the table is listed here. The flow rate and the designed pump head are the given information. In the first step, we calculate the water rise. In the second step, we calculate the head loss. In the third step, we calculate the system head. In this table, we could find that when Q is equals to 0.75 cubic meter per second, the designed pump head is equals to the required energy provided by the system. So which means that in 0.75, the H sub P is equals to the system head. Therefore, the flow rate should equals to 0.75 cubic meter per second. We can also use a plot to find the flow rate. We could find that in this plot, when the pump curve and the system curve interact, at the point when Q is equals to 0.75. So currently we have the value of the flow rate. Then we can calculate the velocity. The velocity is equals to Q over A. Therefore, we can calculate the velocity is equals to 3.82 meter per second. Let's move on to the problem 2. Here is a transmission system transport water from reservoir A to reservoir D. We know the water surface elevation in reservoir A is equals to 100 feet, and the water surface elevation in reservoir D is equals to 150 feet. The Darcy-Weisbach friction factor is equals to 0.02 for all the pipes. We know the length and the diameter for each section of the pipe, and we also know the pump characteristics. This problem asks us to calculate the total flow rate and the pump head. And it also asks us to calculate the flow rate in pipe BC1 and pipe BC2. So to solve the total flow rate, we can apply the equivalent pipe method to replace the pipe BC1 and pipe BC2 by using an equivalent pipe BC. By applying the equivalent pipe method, we need to solve 3 unknowns: the equivalent diameter, friction, and length. We need to randomly assign the value to 2 of them and calculate the third parameters by applying the equation. Because pipe AB and CD, they have same diameter, which is equals to 3 feet, and the same friction factor equals to 0.02. Therefore, we assign the diameter, it also equals to 3 feet, and the friction factor, it equals to 0.02. Then by applying the equation 3.47, we can calculate the value of the equivalent length of pipe BC. It equals to 652 feet. So the second step is to find the equivalent pipe for the pipe AB. Because the diameter in each section of the pipe are the same, and the friction factor are also the same in each section of the pipe. Therefore, the equivalent length of pipe AD is equals to the length of pipe AB plus the equivalent pipe BC plus pipe CD. It equals to 5,792 feet. So currently we have the water elevation in reservoir A and reservoir D, and we just calculate the equivalent diameter, friction factor, and the length of the pipe AD. Therefore, the next step, we can calculate the system curve equation. So the first, we need to calculate the water rise between reservoir A and D. It equals to 50 feet. The next step is to calculate the head loss between these two reservoirs. The friction loss is equals to the K times Q to the power of M. According to table 3.4 for Darcy-Weisbach equation in British system, we should pay attention to this part because in this problem, it is the British system. Therefore, the coefficient to calculate the value of K should be different with the equation that we used in the first problem. So in this problem, the K it equals to 0.012. and the head loss, it equals to 0.012 times q to the power of 2. Then we can get the system curve equation. It equals to the water rise plus the head loss. It equals to 50 plus 0.012 times q to the power of 2. So currently we have the head loss and the system head. Then we can bring the value of the flow rate provided in the pump characteristics into these two equations. Then we can get the table which is listed here, summarize all the informations. In this table, we cannot directly to find the point where the designed pump head equals to the system head. So let's take a look at the plot, which is much more easier to find the intersection point. We could find that in the axis value of the intersection point, it ranges is between 10 to 12. Therefore, we need to do the interpolation between these 2 points to find the specific value of this intersection points. We could find that when the Q equals to 13.5, the pump head and the system head are all equals to 52.2. Therefore, the flow rate should equals to 13.5 cubic feet per second, and the pump head, it equals to 52.2 feet. So currently we have the flow rate, total flow rate, it equals to 13.4 cubic feet per second. For the equivalent pipe BC, we already know its diameter, friction factor, and length. For the original pipe, BC1 and BC2, we also know the value of these 3 parameters. Therefore, the next step, we can use the friction loss equation to calculate the flow rate in BC1 and BC2. Let's use the parameters in equivalent pipe BC to calculate the value of the head loss between BC first. According to the equation in table 3.4, we can calculate the value of head loss between point B and C. It equals to 0.246 feet. The next step is to use the pipe BC1 and BC2 to represent the head loss between B and C. If we applying the pipe BC1 to calculate the head loss, it equals to K times Q to the power of 2. And we can calculate the value of K BC1 according to table 3.42. Because in the previous step, we already know the value of the head loss between BC. We can bring the value 0.246 feet into this equation. Therefore, we can calculate the flow rate in BC1. It equals to 20.5 cubic feet per second. We can, following the same procedure to calculate BC2, it equals to 1 cubic feet per second. Or because the total flow rate, it equals to 30.5 cubic feet per second, and the flow rate in BC1, it equals to 12.5 cubic feet per second. We use Q minus QBC1. We can also get the QBC2, it equals to 1 cubic feet per second. Let's move on to the problem 3. Here is a pipeline conveying water from reservoir A to B. We already know the difference of the water surface elevation in reservoir A and reservoir B. It equals to 196 feet. We also know the friction factor, length, and the diameter of the pipe. In this problem, the minor losses can be negligible, therefore the head loss equals to the friction loss. In this problem, we need to determine the flow rate and the energy head added to the flow by each pump if two identical pumps are used in series. And the pump characteristics are tabulated below. Although this problem used two pumps, but to solve this problem, we still need to use the system curve equation. So the first step is to calculate the flow rise. It's already given, it's 196 feet. The next step is to calculate the head loss between the two reservoirs. It equals to K times Q to the power of M. According to the equation given in table 3.4, we can get the coefficient K, it equals to 0.916. Therefore, we can use M and K to represent the head loss. It equals to 0.916 times Q to the power of 2. And then we can get the system curve equation. The system head, it equals to 196 plus 0.916 times Q to the power of 2. After we use the flow rate to represent the head loss and the system head, then we can bring the flow rate back into these two equations to calculate the specific value of the head loss and the system head. So the next step, we can use a table to summarize all the information that we got. Because in this problem, we use two identical pumps used in series. Therefore, the discharge through the two pumps must be the same, should equals to Q. And the total pump head should equals to 2 times each pump head. In this plot, we could see that when the Q equals to 15, the pump curve and the system curve are interact with each other. So when Q equals to 15, the total pump head, it equals to the system head. We could determine that the flow rate, it equals to 15 cubic feet per second. And the pump head for each pump is around 201 feet. Okay, let's take a look at the problem 4. It is also a two-pump problem. In this problem, we already know the water surface elevation in reservoir A and B. We also know the length, diameter, and friction factor in the pipe. And we also know the coefficient of the minor losses. The minor losses are come from the entrance, the discharge, and the valve. We know the flow rate and the pump head when there is a single pump, and also know the pump characteristics. We want to know the flow rate if two identical pumps are used in a parallel combination, and the flow rate in a series combination. So to solve this problem, first, we need to calculate the system curve equation. The water rise, it equals to the difference of the water surface elevation between the two reservoirs. It equals to 47.4 meter. The friction loss in pipeline AB, it equals to K times Q to the power of M. Based on the table 3.4, we can calculate the value of K, it equals to 98.3. Because we already know the value of M and K, we can represent the H sub F. Because in this problem, we also need to consider the minor losses. So the next step is to calculate the minor losses. It equals to the coefficient times the velocity head. Then after we bring the value back into the equation, we can get the minor losses. It equals to 5.3 times Q to the power of 2. So currently, we have the friction loss and the minor loss and the water rise. Therefore, we can calculate the system curve equation. The system head, it equals to water rise plus the head loss. The head loss, it equals to the friction loss plus the minor losses. So currently, we can use the flow rate to represent the system head. Therefore, the next step is to summarizing data into a table. So let's take a look at the first situation, which is to to locate the two pumps in parallel. Because the two identical pumps are used in parallel, therefore, the total flow rate equals to 2 times the single flow rate. In the plot, we could find that when total flow rate equals to 0.6, the pump head equals to the system head. Therefore, the total flow rate Q prime should equals to the 0.6 cubic meter per second, and the pump head, it close to 85 meter. Now let's summarize the data into a table when the two pumps are located in series. In this situation, the total pump head should equals to 2 times the single pump head. Let's take a look at this plot. When the Q equals to 0.75, the total pump head, it equals to the total system head. Therefore, the flow rate equals to 0.75 cubic meter per second, and its corresponding total pump head, it equals to 105 meter. Let's move on to the problem 5. It's a pumps and branching pipes problem. In this problem, for all the pipes, their length, it equals to 1060 meter. Their diameter equals to 1 meter, and their friction factor equals to 0.02. The water surface elevation in reservoir A equals to 26.2 meter. And in the reservoir D, it equals to 33.5 meter. We know that the flow rate in pipe BC, it equals to 0.5 cubic meter per second. In this pipeline system, there are two pumps. The first pump is in pipe AB. The second pump is in pipe BC. These two pumps are identical, and we already know the pump characteristics. So based on those given information, this problem wants us to calculate the flow rate in pipe AB and BD. And it also wants us to determine the surface elevation in reservoir C and the head for each pumps. Because we already know the surface elevation in reservoir A and D. Therefore, we can calculate the system curve equation from reservoir A to D. So first step is to calculate the water rise between reservoir A and D. It equals to 7.3 meters. The next step is to, because the reservoir A and D is linked by the pump AB and BD. Let's take a look at the AB first to calculate the head loss. It equals to K times Q to the power of M. Based on the equation given in table 3.4, we can calculate the K, it equals to 2.64. Therefore, we can use the flow rate to represent the head loss between reservoir A and junction B. It equals to 2.64 times Q to the power of 2. The next step is to calculate the head loss between junction B and reservoir D. Because the flow rate in pipe AB is the total flow rate. It equals to the flow rate in pipeline BC plus the flow rate in pipeline BD. Because we already know the flow rate in pipe BC, it equals to 0.5. Therefore, the flow rate in pipe BD can be represented by Q minus 0.5. Because the length, diameter, and friction factor for all the pipes are the same. Therefore, we do not need to recalculate the coefficient K. We can directly use the flow rate in pipeline BD to represent the head loss. It equals to 2 times 64 times Q minus 0.5 to the power of 2. So currently we have the water rise, the head loss from point AB and head loss from point in pipe BD. The next step, we can calculate the system curve equation from reservoir A to D. It equals to the water rise plus the head loss. If we bring the equation into the system curve equation, we can get this value. We can use the flow rate to represent the system head from reservoir A to D. Therefore, we can bring the flow rate in the pump characteristics into the equation. Then we can get the table here. The table lists a given information, the water rise, the head loss from point A to B, and the head loss from point B to D, and the system head from point A to D. From this table and also the plot, we could find that these two curves intersect in the Q between like 1 to 1.25. Therefore, we need to do an interpolation in these 2 points, between these 2 points, to find the specific value of the flow rate. So after we do the interpolation, we will find that when Q equals to 1.1, the pump head is close to the system head. Therefore, the flow rate, the total flow rate, equals to the flow rate in pipe AB. It equals to 1.1 cubic meter per second. And because the flow rate in pipe BD, it equals to the total flow rate minus 0.5, which is the flow rate in pipe BC, we could get the flow rate in pipe BD, it equals to 0.6. And because the flow rate, total flow rate equals to the 1.1 from this table, we could also identify the pump head in pipe AB. It's close to 11.3 meter. And because the pump in pipe BC is identical with the pump in pipe AB, and we know that the flow rate in pipe BC it equals to 0.5. Therefore, from this pump curve, we could identify the head of pump in pipe BC. It equals to 90 meter. So currently, we have the given information about the length, diameter, and friction factor for each pipe. We also know the water surface elevation in reservoir A and D. We also know the flow rate in pipe BC. Based on the previous calculation, we know the flow rate, total flow rate, equals to the flow rate in pipe AB equals to 1.1 cubic meter per second, and the flow rate in pipe BD, it equals to 0.6 cubic meter per second. We also know the head for these two pipes, and we also get the relationship between the head loss in pipe AB with the flow rate in pipe AB. Because we already know the flow rate in pipe AB, it equals to 1.1. If we bring this value back into this equation, we could get the head loss in pipe AB, it equals to 3.19 meter. And similarly, we can get the head loss in pipe BC, it equals to 0.66 meter. So the next step, let's considering to calculate the water surface elevation in point C. So to do that, we need to use the energy equation from point A to B. Because the total energy at point A plus the energy provided by the pump equals to the total energy at point B plus the head loss from point A to B. If we bring the value back to this equation, we could get the total energy at point B close to 34.31 meter. If we consider the energy equation from junction B to the reservoir C, we could get the total energy at junction B plus the power contributed in pipe BC equals to the total energy at reservoir C plus the head loss between B and C. After we bring the value back to this equation, we could get the total energy, which is also the water elevation in reservoir C. It's close to 52.65 meter. Now let's take a look at the last problem, which is also pump and branching pipes problem. In this problem, we know the water surface elevation in reservoir A, B, and C. We also know the pipe and pump characteristics. It asks us to calculate the flow rate in pipe 1, 2, and 3. Based on the given information, we know that the water surface elevation in reservoir A and B are lower than the reservoir C. And there are also 2 pumps in reservoir A and B. Therefore, we can determine the direction of the flow in the pipe is from reservoir A and B to the reservoir C. So let's take a look at the path from reservoir A to reservoir C first. We can calculate the water rise between these 2 reservoirs. It equals to 20 feet. And the head loss in pipeline 1, it equals to K times Q to the power of M. And we can, based on the equation in table 3.4, we can calculate the K, it equals to 0.126. Therefore, we can use the flow rate in pipe 1 to represent the head loss in pipe 1. And then we can calculate the head loss in pipe 3. So similarly, based on the same procedure, we can get the head loss in pipe 3. It equals to 0.0774 times Q3 to the power of 2. So currently we have the relationship between the flow rate and the head loss in pump 3. The pumps in pipe 1 and 2 are all contributed to overcome the head loss in pipe 3. If we can describe their contribution respectively and then considering their composite effect, their composite effect should equals to the head loss in pipe 3. Therefore, based on that interaction point, we can determine the value of the flow rate in pipe 3. So to do that, we introduce a new term, which is called the net pump head, for describing the contribution from each pump to overcome the head loss in pipe 3. So originally, the pump head contributed to lift the water and overcome the head loss. So the net pump head only describe the contribution to overcome the head loss in pipe 3. So it equals to the pump head minus the water rise minus the head loss in pipe 1. So currently we have the value of the water rise and we use the flow rate to represent the head loss in pipe 1. If we bring this value or equation back to this one, we can get the net pump head equals to the pump head 1 minus 20 minus 0.126 times Q1 to the power of 2. Let's take a look at the path from reservoir B to C. Similarly, first we need to calculate the water rise from these 2 points. It equals to 40 feet. Then we need to calculate the head loss in pipeline 2. Based on the equation given in table 3.4, the coefficient K, it equals to 0.141. Then we can use the flow rate to represent the head loss in pipe 2. Similarly, the pump 2 also contributed to overcome the head loss in pipe 3. Therefore, we use the net pump head to describe the contribution by the pump 2 to overcome the head loss in pipe 3. So it equals to Pump head 2 minus 40 minus 0.141 times Q2 to the power of 2. So let's summarize all the information into a table. In this table, we list the flow rate, the pump head in pump 1 and 2, and their net pump head respectively. So this plot shows the single pump head, the net pump head by the single pump, and the head loss in pipe 3. In this plot, the red and the blue line represent the net pump head. As we just mentioned, the net pump head describes the contribution provided by a single pump to overcome the head loss in pipe 3. And the yellow line describes the combined pump curves. We calculate the yellow line by adding the corresponding flow rate with the same pump head on the red line and the blue line. For instance, the distance between the y-axis and the purple dot, we represent it by x. This distance should equal to the distance between these 2 points. In this plot, we can also find that the combined pump curves intersect with the green line, which represents the head loss in pipe 3, when the flow rate close to 34 cubic feet per second. Therefore, we can read its corresponding pump head close to 90 feet. And because it is a parallel system, the pump head in each pump should be the same. Therefore, we can draw a horizontal line, and this line intersect with the red line and the blue line. Then we can read the flow rate in pipe 1 close to 22.5 cubic feet per second, and the flow rate in pipe 2 close to 11.5 cubic feet per second.